It's hard to study what's inside planets, but sometimes we get lucky. We might have just learned something surprising about the interior of Uranus. And no, it has nothing to do with the bizarre tilt of its axis. This story comes from a new paper in the journal Nature Astronomy. We know that Earth's core is mostly iron and nickel, and while we can't see inside Uranus, we can model what's going on beneath its clouds by studying how seismic waves move through the planet. The models suggest that Uranus' core isn't like Earth's. It's way less dense. In fact, it's so light that it's almost fluffy. So what's going on here? Is Uranus a failed ice giant? Ice giants are the next step up in complexity from gas giants. Neptune and Jupiter are examples of gas giants. They have no solid surface on which to stand, only a gradually thickening atmosphere that eventually becomes a liquid slushy. Ice giants, though, they're different. They're big enough for their atmospheres to become a thick slushy, but also for there to be actual solid ground. Saturn is our only example of an ice giant because we haven't found any definitive evidence of others out in the universe. But scientists expect them to exist, and Uranus may actually be one. The problem is that it doesn't seem to fit the ice giant description. Scientists think Uranus should look more like a mini Neptune, but it's smaller than predicted, and it's missing some key features like a substantial atmosphere. For a long time, astronomers assumed that Uranus was just made of less stuff than expected, kind of a failed ice giant, but recent studies challenge that idea. Take this 2021 paper, for example. A team of scientists developed a new model of Uranus and concluded that its interior looks surprisingly similar to Saturn's. They just needed a lot less atmosphere. And this new paper adds another piece to that puzzle. It suggests that Uranus does have a solid core after all, just not one made of iron like Earth's. But wait, if ice is mostly empty space, how can we talk about its density? We could take the average density of water, which is about 1 gram per cubic centimeter. And that would make the average density of Uranus' core about 0.3 grams per cubic centimeter, which is still too high. There's something else going on here, so let's explain how we know this in the first place. Studying the insides of planets without actually going inside is all about indirect evidence. The main tool in planetary seismology is finding natural sources of seismic waves, much like earthquakes, that shake up a planet and send these waves rippling through its insides. If we know how fast these waves move, we can use that to infer the properties of the materials they're passing through. And for planets without an atmosphere, like Mercury, we can actually detect these waves by listening carefully. But Uranus has an atmosphere, a very thick one, at least compared to Earth's. So detecting seismic waves directly is pretty difficult. Instead, scientists turn to the next best thing, looking at the planet's rings. Whenever seismic waves hit a boundary between two different kinds of material, they get partially reflected and partially transmitted. And as they pass through the planet, they can cause the planet's rings to darken and brighten. By looking closely at the rings and matching the brightness variations to known frequencies, researchers can identify which waves are hitting which boundaries and how fast they're moving. Using this technique, scientists measured the speed of seismic waves as they passed through the boundary between Uranus' core and its mantle. Now, if the core were made of iron like Earth's, we'd expect it to be quite dense. And if it were denser, the seismic waves would slow down as they hit the core. But they didn't really slow down. The data fits better with a fluffy, low-density core. This is super weird because based on its size, Uranus' core should have enough gravity to squeeze all of its mass into a very small space. Instead, it seems to be taking up nearly half the planet's entire radius. It's like trying to fill a basketball with air. You can blow up the skin of the ball until it's barely over a centimeter thick, but it takes a lot more air to fill up the whole volume. Could this be the real reason Uranus is such a bad basketball? It's not clear exactly what's going on here. One possibility is that Uranus started out as a larger, hotter ball of gas that had enough gravity to crush hydrogen and helium into metallic form. Metallic hydrogen is electrically conductive and acts like a giant battery. And that electricity then somehow caused the magnetic field that makes Uranus such a strong magnet. Over time, the metallic hydrogen in the core crystallized, forming a strange form of ice. This ice could then insulate the core, causing it to puff up and stop conducting. Eventually, the insulating core would cool the rest of the planet down enough for regular ice to start forming in the mantle. That ice would eventually make its way to the surface and become the familiar Uranus we know and love. Now, this may sound like a reasonable explanation, but it comes with its own set of problems. Metallic hydrogen is tricky, like it exists only under extreme pressure and temperature, and once it cools, it loses those properties and turns into a regular old insulator. So it needs to somehow maintain that state for billions of years. Plus, all the hydrogen in the universe tends to be pretty well mixed with helium. So if Uranus' core started out as pure hydrogen, that wouldn't really make sense. There is one other option. Maybe Uranus really is a failed ice giant. Perhaps it never had enough mass to crush hydrogen into that metallic form. But if that's true, it is kind of a stretch to imagine how Uranus would be able to keep its core hot enough to prevent ice from forming inside it. Either way, there's clearly something odd going on with Uranus' core. To figure out what exactly, we'll need more data. NASA's sending a probe named Dragonfly to investigate in the 2030s. Its mission is to find out if life ever existed on Titan, Saturn's largest moon. But Dragonfly will also fly past Uranus and perform its own ring-based seismology experiment. It won't be able to measure the speed of seismic waves directly, but it'll be able to measure the change in brightness of Uranus rings at a bunch of different frequencies. So hopefully we'll learn what's going on inside this sideways planet. And when we do, maybe we'll finally get to the bottom of why it's such a bad basketball. Speaking of things we don't understand, thanks for watching this episode, which was brought to you by our incredible community of patrons. You all make it possible for us to bring mind-blowing science to everyone for free. If you'd like to be involved, you can check out our support page.